Hi guys. Today we're going to talk about the trends that the periodic table organizes for us so that we can see them really well. So different elements have different characteristics, and there tends to be patterns in these characteristics that the elements show. And so the periodic table organizes these really nicely so that we can understand how different elements are going to interact with each other. So the first one we're going to look at is actually something that we've kind of already been talking about. I'm going to move me out of the corner here so we can totally see all our notes. There we go. And so here we're talking about shielding effect. And we haven't used that term yet, but we actually have been talking about it, because what shielding is that we have the nucleus in the center, and as we add these electrons at that lowest energy level and then higher and higher energy levels, the electrons that are at those higher energy levels that are further out from the nucleus are blocked or shielded by the electrons that are closer to the nucleus. And so here's our definition of shielding. And you can pause the video now and get that into your notes. Okay, so we see here that valence electrons, remember valence means outer level electrons, are being shielded by that core or inner level electrons. So as we go across a period, so across a row, and here we're looking at level 3 or period 3, with sodium and magnesium, aluminum, silicon, phosphorus, sulfur, and chlorine. As we go across, the shielding effect stays the same. That's because we are adding electrons at the same energy level, and we're not changing the number of electrons that are between that energy level and the nucleus. So as we go down a group or column, we see that shielding effect increases. And this makes sense because we are adding electrons at different energy levels. So here we're looking at column 7, and we're looking at fluorine, chlorine, bromine, iodine, and acetane. And we see fluorine is at level 2, chlorine's at level 3, bromine's at level 4, and so on. And we can see this if we actually look at the periodic table. We see that each of these add their valence electrons are at higher energy levels. So the shielding effect is increasing. And remember, you can pause this video at any time to take notes. We've actually talked a lot about, as we were talking about the periods and the energy levels, and we were talking about adding electrons at different energy levels, that we were making the atom bigger and bigger because we are literally adding layers to the atom. And so here's how we actually measure it. We measure it from the point of the nucleus in one atom to the point of the nucleus in the other atom that it's bonding to. And then we divide it in half, and that gives us the atomic radius. And the reason that we do that is, remember, we can't actually find electrons. That's the Heisenberg uncertainty principle, that when we use energy to see an electron, it moves because we've given the electron energy, and that makes it move. And so this is how we calculate radius. Now, as we go across a period, across an energy level, and here we're looking at sodium, aluminum, phosphorus, and chlorine, we see that the radius goes down. So as we go across in the periodic table and energy level, the reason that the radius gets smaller is because we're not adding energy levels. Those electrons are being added in the same energy level, but we're adding protons. And protons pull electrons in. The electrons are attracted to the protons in the nucleus. So the more protons there are, the stronger the nucleus is, the stronger the pull on those electrons. And so the electrons come closer and closer and closer to the nucleus. So as we go across the periodic table, we are going to see a decrease in the size of the atom. But as we go down as we go down a group, we see that the radius increases, and this makes sense because we are adding atoms at different energy levels. So fluorine is that electron is being added in the second energy level, chlorine in the third, bromine in the fourth, iodine in the fifth, and then acetine is in the seventh. Oh, was iodine in the sixth? Iodine was in the sixth. Acetine is in the seventh. Now notice we have a little D. All right, so our next trend we're going to look at is ionization energy. I'm going to give you a minute to write this definition down in your notes. The amount of energy needed to remove an electron from an atom. So if an atom has a high ionization energy, that means it's very difficult to remove an electron from that atom. If an atom has a low ionization energy, that means it requires very little energy to remove an electron from that atom. What we're seeing here by this graphic is we're saying if we have a big atom and we exert some energy, we will result in a smaller atom and an electron being removed. So this electron is going off. And here we see our atom is now positively charged because the atom has lost an electron. That electron has left. So it requires some energy to remove an electron from an atom. And it just depends on how much energy. And so here we go. Going across a period or energy level, we see that ionization energy increases. This is because that nucleus is getting stronger. We're adding more protons, so the nucleus is stronger and the electrons are attracted to it. And so the overall trend, you'll see there's some little changes there. We're not going to worry about them right now. That's something to talk about if you take AP Chemistry. We look at that. But basically, as we go across the periodic table from left to right, we're going to see that ionization energy increases. It is harder to remove an electron from chlorine than it is from sodium. And it's the hardest to remove electrons from those noble gases, that eighth column. They do not like to give up electrons. Excuse me. And so as we go down a group or a column, we see that ionization energy decreases. And this is because of that shielding effect. As we go down the column, electrons are getting further and further away from that nucleus, so they have less attraction to it, and it's easier to remove them. So when we look at beryllium in the second energy level, it requires a lot of energy to remove an electron from beryllium because that electron is so close to the nucleus. But the further away we get from the nucleus, and here we are looking at barium. Barium is much easier to remove an electron from its nucleus because that electron is all the way out in the 6th energy level, much further away. All right, so our next and final trend that we're going to look at in Chemistry 1 is electronegativity. Let's write that definition down in our notes. The ability for an atom to attract electrons to itself when it's combined with another atom. So electronegativity means how much energy do you exert to take away an electron from another atom? Basically, like how attractive are you to another atom? So ionization energy is how much energy does it take to remove an electron from an atom. Electronegativity is how good are you at removing an electron from an atom. So if you have a high electronegativity, then you are a very attractive atom and very good at stealing electrons away. If you have very low electronegativity, not very attractive, and you have a hard time stealing electrons away. So as we go across a period or an energy level, our electronegativity is going to increase. And that is because there is that greater nuclear pull. We're going back to adding those protons, right? As we look across this 3rd energy level here, sodium, magnesium, aluminum, silicon, and so on, each one of these, all their valence electrons are at the 3rd energy level, and we are adding a proton with each one of them, right? Magnesium has one more proton than sodium. Aluminum has one more proton than magnesium. And so with each proton, that nucleus gets stronger and more attractive, and so other atoms will give up their electrons more easily to chlorine than it will to sodium. Our only exception is noble gases. Their electronegativity is 0, so noble gases are here in the 8th column. After chlorine is argon, and argon electronegativity is 0. They are inert. They are unreactive. So that's the only exception to that rule. Now, as we go down a group, electronegativity is going to decrease again because of that shielding. Larger atoms have less pull on their own and other atoms. So the same reason ionization energy decreases, electronegativity decreases. So fluorine, looking at the 7th column here, the halogens, fluorine only has 2 energy levels, not a lot of shielding, so that nucleus is pretty exposed. And so fluorine's nucleus can attract other electrons from other atoms. But as we go down and we look at like iodine, iodine is at energy level 5, and so it has much greater shielding, so it's harder to see its nucleus, and the atoms, the electrons from other atoms have a hard time being attracted to iodine. Okay, guys, so here we're going to summarize our trends actually on the periodic table. So turn to the blank periodic table in your notes, and we're going to draw on our periodic table to show these trends. And so shielding effect stays the same. You can just write that across the top there if you want as we go across the periodic table. Let's look at atomic radius first. And we're going to see it decreases. So to represent atomic radius, we're going to do some green circles, and we're going to show them getting smaller. There we go. And you want to make a little key on your periodic table. I'm going to put mine just right next to that word right there, but you want to draw it somewhere on your periodic table to show the green ones are radius. Now I'm going to change my color to blue for ionization energy. And ionization energy increases as we go across our periodic table. And then for electronegativity, I'm going to choose red. And it also increases. So I'm going to draw bigger and bigger circles as we go across there. So here we see radius decreases, ionization energy increases, electronegativity increases as we go across the periodic table. If you need to pause the video right now so that you can get this down, go ahead, because next we're going to look at it going down the periodic table. Okay, so here we are looking at trends going down the periodic table. We're going to do the same thing. I'm going to bring up my drawing tools here. And so let's see, we had green for our atomic radius. And so we're going to draw a small one up here and a little bigger going down and a bigger one down here. And put our little key here so we know green means atomic radius. We can also use green for shielding effect because the two go together. As we're adding those electrons at further out energy levels, we're increasing that shielding effect. And this is where you get the snowman, like people picture a snowman for the radius. And then I believe we had blue for our ionization energy. So I'm going to use a blue oval. And for ionization energy, we start out bigger up top and we get smaller as we go down because of the shielding. Those electrons, as we add them, are shielding those outer electrons from the nucleus. So there's all these extra electrons in there, and these outer electrons can't see the nucleus, and so it's pretty easy to steal them. Therefore, low ionization energy. And then I think our last one, right, electronegativity was red, and electronegativity up top, much bigger, and as we go down the periodic table, it gets smaller, again because of the shielding effect. So other atoms, electrons, cannot see the nucleus that's deep down inside there and shielded by all those extra electrons, and therefore they're not very attracted to the nucleus of these bigger atoms. But up here where there's very little shielding, these electrons can see the nucleus, and so this guy is very attractive to the smaller atoms' nucleus. All right, so there ends our Unit 3 notes and our notes on the trends of the periodic table.